Welcome to lesson 3-2. Yesterday in lesson 3-1 we worked on adding and subtracting radical expressions and simplifying. So in lesson 3-2 we're going to work on multiplying and dividing radical expressions. So those are actually our learning targets. We have to first multiply and divide rational expressions, and then with dividing we also have to do a process called rationalize the denominator, and so we'll learn what that is and when to do that. So the first couple tables on this front page are going to have us discover some of the properties for multiplying radical expressions. So we're going to complete the table, and so if A is 4 and B is 9, they want us to look at the square root of 4 times the square root of 9. Okay, so we want to look at that. And then if you look at the next column, it says, well, what is just A times B? Well, 4 times 9 is actually 36. So if we took the square root of A times B, that's asking us to take the square root of 36, which is 6. Okay, which we would also get if we took the square roots individually. So the square root of 4 we know is 2, and the square root of 9 we know is 3. And 2 times 3 also gives us 6. Okay, so because we don't have a lot of room, I just wrote it in the lower column. So we're really not answering this question. But let's go ahead and try the next one. We'll do the 9 and the 16 just to see that it actually does work. So if I were to take the square root of 9, and I were to multiply this by the square root of 16, I could do those square roots individually. And that would give me 3 times 4, which is 12. Okay. But if I multiplied the 9 times the 16, if I did that, I would actually get 144. And we also know that the square root of 144 is 12. So we're going to get 12 either way. Okay, so that should give us a rule that we can highlight. So it says, write an equation that relates the square root of A, the square root of B, and the square root of AB. So basically, the square root of A times the square root of B is going to equal the square root of A times B. What it means is we can multiply what's inside the radicals together. Okay? And they don't have to be like terms, like when you're adding or subtracting. It doesn't matter what's in the radicals. They do have to be the same index, like both square roots, both cube roots, but you can multiply them inside. And once you do that, you typically have to simplify as well. Okay, so now in our part C, it says, well, all the values of A and B in part A were perfect squares. But in the table below, they want us to choose some values for A and B that are not perfect squares. Okay, and then we could use a calculator to show the same equivalencies that we saw for part A. Okay, so I'm just going to make some numbers up. Let's just say, A is 3 and maybe B is 5. Okay, so if we did the individual square roots, like if we looked at the square root of 3 times the square root of 5, if I did that on my calculator, okay, I would get kind of a messy number. So if I did that individually, the square root of 3 is about 1.7. Okay, it's a little more than that, but it's about 1.7. And then the square root of 5, is about 2.2. Okay, so if I multiply those together, okay, I get about 3.8 or 3.9, somewhere in there. Okay, but if I actually multiplied and got the square root of 15, well, if I try that on my calculator, I also get about 3.8 or 3.9. So it's approximately 3.9, we'll say, in both cases. So using numbers that are not perfect squares, the rule still holds true. So now when we get to part D, the expressions are a little more complicated. We have expressions that have coefficients in front of them. Some are perfect squares and some are not perfect squares. And so we can look at a few of those. So in part A, in column A, we have 2 times the square root of 4. Well, if I think about that, the square root of 4 I know is actually 2. Okay, so that's really 2 times 2. And then that's really the square root of 9, 3. So 2 times 2 is 4, times 3 is 12, which would be the same as if I multiplied 2, the coefficient, and then the insides, 4 times 9, which is actually 36. That's actually 2 root 36. But guess what? The square root of 36 we know. That is 6. we also get 12. So basically the rule is you want to multiply the outsides together and the insides together. And let me show you that. Let's do some yellow, a little brighter. So like 3 root 4 times 5 root 16, the 3 and the 5, those are the outsides. They're going to get multiplied together. And then the 4 and the 16, they're the insides. They get multiplied together. And when you do all that, I think you get, let's see, we do 3 times 5, we're going to get 15 on the outside. And then 4 times 16 is 64, which we can square root out. So that's really 15 times 8, which is 120. Okay, so that's the rule that we want to use. So we want to use outsides together, and then we want to do insides together. And it's the same for the third row. We'll save a little time and skip that one. So next page is where we get our rule. And for our rule, we want to write, first they ask us to write the verbal expression, so a verbal rule. So if I wanted to write it in words, I would say, kind of what I've been saying, multiply the coefficients together, and then multiply the radicands. Or what's underneath the radical. And then, of course, always simplify the final answer. Always simplify. Okay? And so you can see, to multiply any radical expressions together, a root b times c root d is going to give you ac root bd. Okay? And of course, we want to keep our radicals positive, so b has to be greater than or equal to 0, and the same with part d. All right, so basically we just kind of discovered or demonstrated the rules for multiplying. And now we're going to do some practice problems. And these can range from some very simple ones to some ones that are a bit more complicated and need more breaking down. So I'll pick a couple to do. Let's go to the Try These A, which is down the page a little bit. Let's go here to there's some examples above there that I can let you look at if you want to. They're already done. But I'm going to do some of the Try These A with you. So our first one, we're just going to go with our rule of outsides together. So 2 times 5, which is going to be 10, and 10 times 3, which is going to be 30. Okay. Now 30 doesn't really break down, because if I tried to break down 30, I get 2 times 10, 3 times 10, or 2 times 15, but either way, it doesn't break down into any doubles. So if I try to break down 30, let's say I did 2 and 15, well then I get 3 and 5. There's nobody to circle. So that actually is your final answer. Kind of nice when that happens. Okay. But then we get over to part B. Let's do the same thing. 3 times 2 is 6, but then 8 times 6 is 48. And I do believe we can break down 48. If I do primes, it's 2 times 24, which is 2 times 12, which is 2 times 6, wow, and 2 times 3. So there's actually a bit more we can break down. Now I want to circle my primes that are doubles, and so that's going to be 2 times 2 times the 6 that's already out there. So 2 times 2 is 4, times 6 is 24, and then there's a 3 left inside. So we multiplied and then we simplified, and our final answer is always in simplest form. Okay, now in part C, the numbers are kind of big, the 12 and the 18, but I think I would still probably multiply first instead of simplifying individually. So let's just give that a try and see what happens. We may have to do a breakdown. So let's try 4 times 5, so we know that's 20. Okay, and then when we do 12 times 18, so let me go to my calculator, 12 times 18, that's 216. I might check to see if that's a perfect square first. So I might try it out. Is 216 a perfect square? No, it's not. But I am pretty sure I can break it down. So I'm going to go over to the side here and do some prime factorization. So if I divide 216 by 2, I'm going to get 108. And remember, you keep using 2 until you can't anymore. So divide by 2 and I get 54. Divide by 2, that one's going to be 27. I'm done with 2s. I can use some 3s now. 3 times 9, and finally 3 times 3. So the bigger number, the bigger the breakdown could be. All right, so I'm going to circle some primes. I see a pair of 3s. I see a pair of 2s. Okay, so those are going to come out and multiply by 20. So 3 times 2, which is 6, and 6 times 20 is going to be 120. So 120 on the outside. Now on the inside, this is the first time I think we've seen this. There's 2 terms left on the inside. So what you want to do that is multiply those as well. So 2 times 3 is 6. So we end up with 120 times the square root of 6 as our simplest form. Our last example for multiplying radicals together is actually got some variables in it, so we can practice that. So let's do outsides together first. So 3 times 2a is 6a. So I've got 6a. And then I'm going to do a square root of 5a times 15a squared. Well, 5 times 15 is 75. A times a squared is a cubed. Okay, well, a cubed is just a times a times a. That's going to help me do some breakdowns. All right, so 75 is 3 and 25, which is 5 and 5. So I can pull out a 5, and I can pull out an a. 5 times 6 is 30. A times a is a squared. And then left inside, it appears we have a 3 and an a. So we're going to keep a 3a inside. And I think I will highlight this one so it's easy to find. There we go. There's our final answers. Let me highlight our final answers so we can see them a little better. Okay, so that's kind of a good example of the different types of problems you would see with multiplying radicals together. So let's take a breath and think about if you have any questions, make note of them for when we see each other during Zoom, so that when we're going to go on to the division now and do division property of radicals. So division can range from being simple to being a little bit more complex, but basically division of radicals works like multiplication. We're going to divide the coefficients and we're going to divide what's in the radicals, or what we call the radicands. So a root b divided by c root d is going to be a over c times the square root of b over d. And sometimes the b and the d will divide out nicely, and so we don't have to worry about this process of rationalization, so we will see that. Okay, so the index must be the same, square roots and square roots, okay, but we don't have to worry about the radicands being the same like with multiply. All right, so let's take a look at a couple of those. There we go. So we've got some examples here where we're going to do some dividing. Remember, example B is already done for you, so you can take a look at that on your own. I'm going to work on the try these B with you. So for part A, I see 4/5, and that doesn't really divide out at all, so that's going to stay 4/5. But because 42 does divide by 6, I can go ahead and do that. 42 divided by 6 is root 7. That's a great answer. The radical is left, and it's really left as a numerator or a top number. Okay, so that's all right. That's not a problem. Sometimes they divide nicely like that. Now we're going to see that in part B too. So this time 10 does divide by 2, so that's 5. And then root 54 also divides by the root 2 to make a root 27. However, we do need to simplify. So let's do this one short form. I know 27 is 9 times 3. And I know the square root of 9 is, that'll give us another 3 and 3. So I know that's 3. So I want to do 3 times the 5 that's already out there. And then we're going to have a 3 left inside. So 15 times the root of 3. That would be our final answer for part B. Okay, part C, very similar. I'm going to take 12 divided by 3 and get 4. Okay. And then root 75 divided by root 3 is root 25. Okay, but then what is the square root of 25? It's 5. there is no radical left in this problem. Students, though, have a hard time with that. They think they need to have a root left because we usually have a root left, but we don't this time. We just get 20 as our answer. So if it's a perfect square, remember the root goes away. Okay, the last one in this group is part D, and we have 16 divided by 8, and that is going to be 2. Now this time we have a cube root, so we'll keep that in mind. And then we have 8 divided by 1. Well, that's still 8. And x to the 11th divided by x squared. Now remember, with exponents, when you divide, you subtract the exponents. So 11 minus 2 is going to make it 11. Is going to make it x to the 9th. Okay. All right, so we did the dividing part, but now we need to do the simplifying part. Okay, so there with 8, 8's actually a perfect cube. 8 is really 2 times 2 times 2. So all the 2's are going to come out. Okay, and even all the x's will, because you have 3 groups of 3 x's to make 9 x's. So they all come out. So that, again, this is another one where we don't have a radical answer. We have 2 coming out times the 2 that's already there, which is 4. And then all the x's came out, x to the 3rd. So that's the final answer. So now we have all of our final answers for the division problems. So again, all of these problems divided out, so we had no radical left on the bottom. The very last part of our lesson on the dividing is going to be what we call rationalizing the denominator. Okay, and we just have to get in the habit of doing this whenever we see it. So I'll do a couple examples, but we'll see this show up a little more often along the way. So first of all, let's talk about it, what it means. So to rationalize, it means to make rational. You can rationalize the denominator without changing the value of the expression by multiplying the fraction by an appropriate form of 1. Okay, so what we're going to do, and I'm going to go right into an example to show this to you. If you look at part A, you can see that we have square root of 11 divided by square root of 6. 11 does not divide by 6. Okay, so we can't get rid of the radical that way. So we need to multiply by an appropriate form of 1. Well, that appropriate form of 1 would be 6, because it would be root 6 over root 6. Because that's what's going to eliminate the radical when we multiply. So on the top, I get the square root of 11 times 6, or 66. But on the bottom, I get the square root of 36. Perfect square. So that breaks down to root 66 over 6. No radical on the bottom. We just rationalized the denominator. Okay, so that's what we want to be able to do. Let's do another one. Part B. Since there's a root 5 on the bottom, I want to multiply both the top and the bottom by root 5. That's the appropriate form of 1. Root 5 over root 5 is 1. So 2 times root 7 times root 5 is going to be 2 root 35. And on the bottom, you get root 25, because it's 5 times 5. Well, root 25 we know is 5. So we get 2 root 35 over 5. No more radical on the bottom. Okay, so you might not think it looks that much neater, but it's now rational. Okay, we're not trying to divide by a irrational number. Okay, so we'll leave C out for now because the lesson's getting a little long. And I'm going to go into the next page. The top of the next page is just a review of all your exponent powers, power rules and everything. So yes, a very important box, but we've already gone through all of these rules. Okay, and that's because they're going to put some exponents in the next couple of examples for you. So I'll do one of them with you, and then I think the others I'm going to save and kind of do in class with you because this lesson's starting to get a little long. And so I'd really like to finish, I'll just do one of each in number 2. So for 2a, what we see here is a radical with a power of -2. So there's some things to think about. Okay, first of all, we don't ever want a negative power. Okay, never. So one of the things that you might want to do is take that whole expression and maybe move it to the bottom. Okay, so that's one of the things that we could do, is move the whole thing to the bottom. So if we rewrite this, let's go back to pen. If we rewrite this as 1 over the cube root of 8x cubed y to the 6th. But now that we moved it, remember that negative exponent becomes positive. Okay, so now we're looking at it like that. Okay, and so what we end up doing now is we can simplify in a couple different ways. So I'm thinking I want to take the cube root. I notice that all three, 8x to the third power and y to the 6th, are all perfect cubes, because I know 8 is 2 times 2 times 2. I know x times x times x, and I know y times y times y, y times y times y. So everybody comes out, which is kind of nice. Okay, so 2xy squared. So now I have 1 over 2xy squared, but remember that was all still being taken to the second power. So I took care of the radical part of it first. Now I have to pull everything to the second power. So 1 over, and now let's remember 2 squared is 4, x squared is x squared, and this is a multiply right here, 2 times 2, so that's y to the 4th. And that ends up being our final answer. All right, now our very last problem, number 3, wants us to review going from a radical to a fraction power. And that's what they want us to do. Simplify each expression by rewriting it using fractional exponents and exponent properties. All right, so for our last problem, we're going to do part A. So since it's a cube root, remember we want to do power over root. Well, it's 64 to the first, so that's 64 to the power over root, so that's 1/3 power. X has a power of 9, but it goes power over root, so 9/3. So 64 to the 1/3 power, well, 64 actually is a perfect cube because it's 4 times 4 times 4. So that's 4x, and 9 divided by 3 is 3. So we'll spend a little more time on these harder problems in class, and we'll pick some from the homework assignment to go over as well. So if I look on the next page, there's all your practice problems to try. So I want you to look at 4 through 16 and be ready to, star or highlight any that you need me to go over in class. But remember, they're all done for you and posted, so you can work on them and check your answers as you go. Okay, and let me know when you have any questions. I will see you in class.